got a question on the board. So the question is, if an apple falls, does the moon also fall? This is the question Newton asked when he, supposedly saw the apple fall from a tree. Odds are he probably didn't ask it right then and there. Let's be honest. But he sees something falling on Earth, and then he wonders, do those same laws apply elsewhere in the universe? Because the moon's in the universe, right? It's not on Earth, but it should also fall, right? People already knew gravity existed, but this is Newton's way of starting to piece things together and make mathematical sense of it and calculate things mathematically. So, yeah. So does the moon fall? What are your thoughts? Give me a second to think about that. Yeah. Well, it should fall, right? We know gravity exists. Gravity pulls things down. Let's draw some stuff. We're going to draw the Earth here. We'll label it E for Earth. I'm going to draw the moon over here in purple. It's smaller, right? It's out there. This is obviously not to scale. We know gravity pulls things towards the center, right? So the center of the moon should be pulled towards the center of the Earth at all times, right? Why doesn't it hit us? Why doesn't it just crash down and crush us? I mean, I've played Majora's Mask. I know it could happen. So why doesn't that work? We're going to get rid of this moon thing for a minute. So there's a few things at play here on this little piece here. And we've talked about this, I think, before. There's this thing, it's called tangential velocity. We've talked about velocity like all year long. And it's velocity in one direction, right? The moon goes around the Earth, right? So we should actually have left the moon there. I made it smaller this time. And it's kind of following this little orbit here. Nice and not circular. Perfect. So tangential velocity is the velocity that the moon has right here. Because we're kind of following a circle, it doesn't follow perfect circles, but that gets really complicated really fast for physics. Tangential velocity means the moon has velocity going forward. And gravity's pulling it this way. So our vector follows this, right? Our resulting vector. Which is why the moon doesn't actually hit the Earth, because it has forward velocity. And as long as that can be maintained, it doesn't crash into the Earth. The moon actually has slightly more velocity going forward than the Earth can pull in, so the moon's actually slowly moving away from us and eventually will be lost to space. It'll shoot off one day. But I think the sun is set to die before then, so no big deal. We'll all be long dead before then anyway. We're talking billions of years. Yeah, so the moon should be falling, right? It's not falling and crushing us because it has this velocity going forward. This is our tangential velocity. Let's label this. That's just it going forward. And this ends up, because we have the force of gravity pulling it in, is our radial velocity. We're kind of getting into circular rotation here that we're not going to jump right into this today. But that's why the moon's not crushing us like in Majora's Mask. So the moon should fall, right? So you could mathematically do it this way and go, oh look, because it's going forward, it doesn't fall down, but it should be falling down. So Newton wanted to figure out the force of the moon and the earth acting on each other. So he came up with this equation, right? For force, right? We know force is measured in newtons, which are kilograms times meters over seconds squared. So we need a way to take all this stuff into account. I don't know if we need that even, because he does a lot of canceling out. For objects to interact, we need to know the mass of them, because mass is what's giving things gravity. So we need to know the mass of object 1 and the mass of object 2, in our case the Earth and the Moon. It could easily be the Moon and the Earth. It doesn't matter which one's which. The other thing is distance is going to matter here. I don't know how he would have figured this out, but we can talk about how the moon's orbiting Earth, but why doesn't it orbit the sun? The sun has more mass than we do, or Jupiter out there in space has way more mass. Why doesn't that just pull over the moon and be like, you're my friend now, right? So a big thing is going to be distance. We're going to talk about the distance between two objects and their masses. We also need this other thing. It's called big G. I at least call it big G. It's this constant that Newton found. We're going to put it over here. Big G equals this number. It's 6.67 times 10 to the negative 11th. And then he gave it units to cancel some stuff out, which are newtons meters squared over kilograms squared. Right, because we have two masses in kilograms and distance. So our resulting thing ends up being in newtons. So he gave it units. But this is big G. This is a universal constant for universal gravitation, which is not up on the board. As far as we can tell, this works for any two objects in space. Their masses are attracted to each other, and it's all based on the distance, how much they interact. We actually call this an inverse square law. We're going to look at that. I have a little device I'm going to grab. Oh, I'm going to hold it up for the camera. So this thing here is inverse square law apparatus. How it works, it's not going to work because we need so much light to see it. I've got a little solar panel here in the middle that's 1 unit size. It doesn't matter how actually big it is, it's just 1 unit there. And then we can measure the amps of it coming off. They're microamps really because it's so small. And the idea is that we would be in a dark room, we could take a light source, put that like a flashlight, so it's just filling that center square. And then if we move it out one distance, right, because there's about half of each side here. So now there's 4 boxes here. Our distance now, instead of being 1, becomes 2. 2 squared is 4, so we end up with 4 boxes here of the original size. What do you think would happen to this energy reading? It's going to go down by like a 1/4, right? It's not a perfect system, but yeah, it should go down by a 1/4. And then if we move it out 1 more square, again, we get how many boxes then? 1, 2, 3, 4 on each side, so 16 boxes. Plug that in here. We should get basically no energy reading on this by then, because it's now, right, we have 16 boxes, so 16 squared for that number. It's going to go down drastically. And so in an inverse square law, distance is going to make things interact less and less. In fact, if we graph it real fast, like I'm just going to draw a quick graph of what we should be seeing on inverse square law. So here is, right, this should be our interaction. And this is our distance, right? So I'm going to wait, because as distance increases, I have these backwards, right? Distance increases. And this is our interaction. Yeah, interaction here. So what this is saying is our distance increases, our interaction decreases. Pretty drastically too. In reality it should be like down to like nothing pretty quickly. Right? It's an exponentially decreasing curve on there. That's what inverse square law is telling us. So as we get further from a light source, or it's really energy in this case. Can we see that even? Yeah. Energy in here, our light energy, decreases rapidly the further we get from something. In our case, since we're looking at gravity, well, that was our case for our little apparatus there, right? Since we're looking at gravity between 2 objects, the further they are, the less gravity they're going to feel from each other. Which means the moon's kind of locked into hanging out with the Earth for a while, because we're pretty close. As that moon gets further away, because it's slowly getting further from the Earth, eventually it'll be far enough away that that gravitational interaction between the Earth and the moon means that it's negligible, and the moon can just go its own way. And it'll just go off in a straight line, flying forever until it hits something else. You know, depending on where it is in space, it may hit it like another planet and get pulled into there and become one of Jupiter's moons, or may just shoot off into space and never be heard of again. Probably end up around the sun and falling into it eventually, really. But yeah, that's our interactions there. Should we start using this equation and see how it interacts things, how things interact with gravity? Yes. Because now we know what inverse square laws are. We know how things with distance decrease. This is going to be a concept that comes back again when we talk about electrical charges. Coulomb's law looks strangely familiar to this. Okay. So let's set up a problem here. let's set up, let's look at Newton's problems. When he was asking about his question, if an apple falls, does the moon also fall? Let's figure out the force of gravity on an apple. Let's figure that out first, and then we'll go to the moon. So what do we need? We don't know force. We want to find that one. We want to find the force of gravity on an apple. We know big G. We know the mass of, let's say, Earth. We're going to put E for Earth there in the subscript. I have to look it up too. I have it on a piece of paper here. So the mass of Earth is 5.98 times 10 to the 24th kilograms. We know the mass of an apple. It kind of varies by the apple, right? We're going to make our lives simpler and just say the mass of an apple is 1 kilogram. We'll just make our lives easy. And distance. Ooh. How tall do you think an apple tree is? We usually cut them short, so they're not super tall. So let's say 10 feet, roughly. Ooh. Problem is, right, this is a metric system, so we need it in meters. So let's say like 2 meters. And that's about a little over 6 feet. So 2.5 meters. There's about 10 feet. So 2.5 meters for the tree. Ooh. Problem. The apple's not trying to fall to the ground from the tree. The apple's trying to fall to the center of the earth, because that's where the center of gravity is, so it's trying to fall all the way down there. So our distance has to include the center of the earth, which means back in Einstein's day, or Newton's day, and Einstein's day because he came after Newton, but in Newton's day, he had to know the radius of the earth so he could find the center of the earth, roughly, right? So we had to know, right, how far around the earth is to find to the center of the earth the radius of that. So you had to know the circumference of the earth at the equator, right? So you could roughly estimate the radius from the crust that we stand on to the center of the earth. That's what I wanted to say. So we actually need to count that in on this. So the radius of the earth, the value we're using is 6.38 times 10 to the 6th meters. This is followed by, this is moving our decimal place over 6 places, and then adding 250 to that. Does the height of the tree make much difference? Not really, because this is a very large number and this is a very small number. So I'm actually gonna ignore this 2.5 meters. What I really just care about is the radius of the earth, because that's the big number. We're going to end up using a lot of big numbers in this. So if you end up with something like 2 meters above the surface of the earth, it's going to be pretty insignificant, so you can kind of fudge some numbers and ignore some of those small things that don't matter as much. Okay, so let's plug this into our equation here. I'm actually going to move this big G over here, because we know big G, and I want that space. So big G is 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. Okay. So we have the equation, we have all our variables that we need. and ours to find, so I'm just going to start plugging it in over here. Right, we don't know force. We know big G, that's 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. It's a lot to say. And that's going to be multiplied by our distance, or sorry, our mass of the Earth. So we have 5.98 times 10 to the 24th kilograms times 1 kilogram for their mass of the apple, right? All over the distance squared, which is our radius of the Earth. So we have 6.38 times 10 to the 6th meters squared. We can add that 250 in, but in the end, that's going to change our decimal like 10 places down line. I don't care about that one. We're only going to report a couple decimal numbers anyway, so it won't make a difference in our actual answer we get. So plugging this into your calculator is a lot of work. Use a scientific one or a graphing calculator. We're going to work through on this TI-30X. These are the ones I really like to use because they do all the math we really need. And they're only like 10 bucks. So I hope you've got yours out because we're going to walk through how to enter this in, because entering these things in, these big scientific notation numbers and little scientific notation numbers, really is what is impacting student grades a lot, because they don't put things in correctly and get the right answer at the end. So how you enter things is super important. So work through this with me on this one so we can work on that together. So hopefully you've got yours up. If you're using a TI, great to follow along with. Even the one on Google is going to be similar. You may even be able to Google a TI-30X and get something that looks a lot like this one. And then you could like an interface like that and type it in just like you would be using it. If not, even the one on your phone probably works just the same way. Some of the buttons may be out of order. Okay. So when I'm working with big numbers like this, I like to just simplify my equations slowly. I don't like entering it all in at once because then I find I make too many mistakes and I have no idea where those mistakes are. So I'm going to do little bits at a time. I'm actually going to start with this spot here because I actually don't have to plug that into my calculator. Since it's x squared, or kilograms times 1 kilogram, it just becomes kilograms squared, right? So I'm just going to go 5.98 times 10 to the 24th kilograms times 1, right? So kilograms squared is our new unit there. So we have kilograms times kilogram. And then we're going to simplify that bottom one down there. So I'm going to plug into my calculator 6.38. I'm going to hit second. Then we have this inverse button right here. I'm going to push that. That gives me a big capital E, well it's little capital E. And then I'm going to hit the number that comes after the exponent. That big E just stands for exponent, and instead of typing in times 10 to the 24th, I can just hit that E, and it means the same thing. So I can hit E to the 24th. So your calculator should have that, hopefully there. I will write that on this board too. So on my calculator I put in 6.38. I hit the second button on my calculator. Then I hit the button that looks like it's the inverse button, and up above it, it has E in capitals. And it's above number 7. Down here is button 7. Okay, just so it's easier for you to find, that's what one I'm pushing. And then I put in 24. Then I'm going to hit equals, just so it sticks together, because then I don't have to worry about putting parentheses, because we need to square this number. So it, does that number. Then if I hit the squared button on the side on the left by number 7 also, it's a smaller button right here, and it says x squared. If you push that button, it gives you answer squared. So you just hit enter then, and now it's squared that number for me, this number here. So I end up with 4.07044 times 10 to the 49th. Whew, big number. Keep in mind, Newton did not have a calculator. He would have done this all on paper and in his head. Crazy. Okay, so I'm going to put this number down, 6.67 times 10 to the negative 11th. That's still newtons, meters squared over kilograms squared. Oh, I forgot my unit over here. Because we squared these meters, we have meters squared. And a weird parenthesis. Oh, we can cancel some stuff too, right? We could cancel these they're going to cancel. So we're going to be left in newtons for our force. I mean, we shouldn't cancel until we're doing the math. Whatever. Canceling them now. Okay, so my next step from there is I'm going to plug in that number and divide it. I'm going to get rid of all this stuff. If you need it again, you can always rewind. So on my calculator, I'm going to plug it in exactly this way. I'm going to put in a parenthesis, which is above number 8. I'm going to put parenthesis, 5.98 e to the 24th, parenthesis, then I'm going to hit times. Oh, no, not times, sorry, we're dividing. Dividing by 4.07044 times 10 to the 49th. Right, so e is the 49th. I want to plug this into my calculator just as it says there. So parenthesis, open parentheses, right? 5.98, second inverse, now we have the exponent button, 24, close the parentheses, divide by, open a parenthesis, 4.07044, second inverse, so it gives me the E button to the 49th, close parenthesis. So over here, we should be left with 1.469, and it goes on. I'm going to leave it at 4.9, or 1.4691 times 10 to the negative 25th. Okay, so I'm going to erase some of this, like all that. We still have big G out here, right? We have the 6.67 times 10 to the negative 11th. We're down to newtons because I canceled things out early. To get our force. So I'm going to plug it in just as it shows there, right? I'm going to put things in parentheses though, just because I really like sticking numbers together when I'm working with these exponentially large and small numbers. It keeps things simpler for me so I don't make mistakes. So I'm going to put a parentheses, open parentheses, 6.67, second inverse, so you get the exponent button. Instead of hitting, some students hit the minus button, hit the negative button down here on the bottom. So we have negative 11. It makes a difference. Your calculator would subtract 11 from numbers versus trying to put it in there as a decimal number. So you have to hit that negative number, not subtraction. I think it just gives you a syntax error if you hit subtract. So it makes a difference. So we've got this plugged in, and then I close that parentheses, so I'm going to hit times 1. I want open parentheses, so 1.4691 inverse, right? So second inverse, give us the exponent, and I put in negative 25. Enter. Did something wrong. I came up with 9.79 times 10 to the negative 36, which I know is not right. So I made a mistake somewhere. See why I write everything down and why I am able to go back now. Yeah, I don't know what I did wrong. This is why you write things down step by step, and I do it slowly, because I knew this number is wrong in my head, but I have to be able to go and check my work. And I did not make this mistake on purpose. This is all on accident. So if you were following along, sorry, mistakes happen. This is why we're doing it this way, though. And it's a nice, happy accident. So what I did is I went and troubleshot some of my work. I replugged this into my calculator. The 6.38 times 10 to the 6th squared. Before, somehow I got to the 49th, which doesn't make sense to me now that I'm looking at it, and it shouldn't have made sense to me then. This 49th is way too big of a number. It's actually, I don't know how I got 49, it should be 13. So I'm just going to replace it with a 13, and I'm going to leave it in a different color so we can see that was a mistake that I made. And so now we don't have to do our whole problem over. We figured out where our mistake is. So all I have to do is fix this little bit here. So I'm going to replug that into my calculator of 5.9 times 10 to the 24, right, our second button, right? And we're going to divide that by whatever 4.07044 inverse, so we get to the 13th. A lot of times buttons stick on the calculator, so you miss some of those. Like instead of 13, I almost put in 1. Would have made a difference. So I still get 1.4691 repeating, a long one. But instead of the negative 25th, I get a much more reasonable number of the 11th. Okay, so I'm going to take that number and I'm going to multiply by the 6.67 to the negative 11th, which then those negative and positive 11s can cancel each other out. And so now I get a force equaling 9.799. And it kind of keeps going. And this is in newtons. Does that number look familiar? Because it should. It should look an awful lot like our value for little g, right, which was 9.8. And that was meters per second squared. So this is actually how Newton got the acceleration of gravity because it really only works for things near the center of the Earth or near Earth's surface like we are. In reality, it should fluctuate as we move further away from the Earth, right? Because our distance should grow or shrink if we move towards the center. So this works for near the surface of the Earth, right? Because we used a 1 kilogram object. If we use our old equation, F equals ma, and a is the acceleration of gravity, and we put 1 kilogram in there, and we have 9.8 meters per second squared, our force should then come out to be 9.8 meters per second squared. Nice, right? So this equation here, this little F equals ma, is kind of hidden in here for like objects on their surface. Okay, nice, right? That's how we got his little g from big G. Okay, I said we would do this again for Earth. Earth and Moon. So I'm going to get rid of this other stuff here. Get rid of that. Instead of mass of the apple, we want mass of the moon. There. We know the mass of the Earth still, that's not going to change. And we're going to need the distance between Earth, the center of the Earth, and the moon. Okay. So on my little sheet here, I'm looking for the mass of the moon real fast. That is 7.6 or 7.36 times 10 to the 22nd kilograms. And then we need distance from the Earth to the moon. That's 3.84 times 10 to the 8th meters. So now we should be able to calculate the gravitational force between the Earth and the moon. So let's plug it in. We're going to use our same equation. I'm going to do it just like we did before. So we have 5.98 times 10 to the 24th kilograms, right? Mass of the Earth. And we're going to multiply that by the mass of the moon, which was our 7.36 times 10 to the 22nd kilograms. And then that's going to be divided by the distance squared, so 3.84 times 10 to the 8th meters squared. Instead of writing out big G all the way, right now I'm just going to put a big G and F. And we'll plug in the actual number for big G when we get there. It's just a lot to write out when I have a lot already written in such little space. So I'm going to walk through this on the calculator again if you want to practice along with me. So I'm going to put in 5.98, second E, right, the inverse button here above 7, to the 24th. I hit enter, which gives me now an answer. I'm entering this in a little differently. If you want me to write it out on the board here, this is what I plugged in. I put 5.98, second button, and then my inverse button, right, gives me the exponent then. And then I hit 24. Make my 4 a little more legible. And then I hit the enter / equals button. and then that gives you an answer, and then I just hit times 7.36. Then I do the second, right? Second exponent button, E, 22. Then I hit enter again. Enter equals. I'll move out of the way so you can see all this as I'm doing this onto my calculator. And I'm going to do it all over again. So I hit 5.98, second inverse, so it gives me exponents, 24, oop, I messed up, 24, hit enter, then I'm going to hit times 7.36, actually I want to change this. I'm going to put a parentheses here. Parentheses button, parentheses button. I just worry the calculator may read this wrong, so I go back. You can use the arrow buttons to move around. And hit second in this delete button, which is now insert. If I hit second, I put my open parentheses. Now I hit go back, hit the exponent button, hit 22, close those parentheses, hit enter. So up on top here, in my calculator, I end up with 4.40128 times 10 to the 47th. Oops, 47th. And I'm going to divide that by 3.84 times 10 to the 8th meters squared. Well, this is kilograms squared as well. Okay, and we still need big G. Okay, so I'm going to take this, I'm going to erase all this stuff that I wrote. And again, I'm going to write out what I wrote on there down below, what I'm going to enter into my calculator. So I'm going to take 3.84, my second button, the inverse button. I hope this helps if I write everything out. That's why I'm doing this. So I really hope that you're able to look at this and be like, oh, I know exactly what buttons you pushed. I think it'll help you in the long run. I know it's slow and tedious. So we have 8 there. And then we hit enter or equals, either way, right? It's enter, equal. And so then after we have that, I'm going to push this button here, the x squared button. So that should square our number there. So let's plug that in, 3.84 second e to the 8th equals, then I'm going to square it. And so I end up with, oh right, you got to hit the enter button. In case you need that part there. So I end up with this number here. I end up with 1.47456 times 10 to the 17th. Those are meters squared, and I still have this 4.40128 times 10 to the 47th kilograms squared in big G. So I'm just going to divide those, right? So I put a parentheses button. I'm going to put 4.40128 second button, the inverse button, right? For give me exponents, because they're up above, I wrote them up above, e to the 47th. And then I'm going to push the close parentheses button, then I'm going to push the divide button. My buttons are getting less and less neatly drawn. And then I'm going to have to, come down here because I'm out of room there. Then I'm going to push the open parentheses button again, then plug in the 1.47456. Wow, that was terrible. Hit my second button again as well. Hit these inverse button to give me the exponents again. Plug in 17. Close my parentheses, and then hit enter. Equals. Ready? You're going to plug that in. There's a lot going on there. So second, E47, close my parentheses, divide by, open parentheses, 1.47456. Oop, I missed a decimal, put a 0 instead. Second E17, close parentheses, enter. So over here I have big G still times 2.9848 times 10 to the 30th power. Okay, ready? So don't erase your calculator yet, because here's what I'm going to push next. Wrong color. So taking my calculator as before, I'm not getting rid of that number because I don't want to retype all that stuff in. And multiplication doesn't matter which order you go in, so I'm just going to hit the multiplication button, and then I'm going to plug in big G, which is the 6.67. I'll hit my second button again, the inverse one to give me the exponents. Then I hit, what was it, -11? Not negative, I'm going to hit the button. On this calculator it looks like this. To say a negative number, then I'll hit 1, 1, and then hit enter. Equals. So let's do that. So I'm actually going to put parentheses in here too. I should have done that. I like my parentheses. I probably overuse them, but that's okay. It doesn't change much if you use them and close them correctly. Cool. So this multiplied our answer from before times big G, so you should get our force equaling 1.99 times 10 to the 20th newtons. You might have a rounding difference, but you should be about that number, so roughly 2 to the 20th times 10 to the 20th. Cool. I'm going to stop here because we spent a long time on this. You can plug this in for all kinds of things because we could measure the weight, right, the force of you pushing down on a different planet. Let's say we put you on Neptune. You still have the same mass, but because gravity is different on Neptune, the force of you pushing down on Neptune is different. So we could calculate your weight on Neptune using this equation. We can calculate the pull of Sagittarius A star, which is the black hole in the center of the galaxy, on the Earth. Right? And because of Newton's third law, the other thing we probably should mention, the force that the black hole in the center of the galaxy is putting on the Earth is also the same force that the Earth puts on the black hole. They're equal forces, right? Newton's third law is equal and opposite reactions, actions and reactions. Doesn't matter which one's doing the action, which one's doing the reaction. It's equal and opposite, so same forces applied elsewhere. You pushing down on the Earth is the same as the Earth pushing up on you, right? Newton's third law. But I have that, so you can do all these calculations with this equation. It's really cool. It's universal gravitation. I call it Big G, because Big G is way more fun to say.